Hi, my name is Yanick Volpez, and I'm a PhD student in the Quantum Condensed Matter and Quantum Computation Theory group at the University of Basel. I'm working on topological states of matter with a focus on engineering topological materials. Before going into the details of engineering topological materials, I want to give you a brief introduction to topological states. So there exist different kinds of topological states, and I will explain one example that highlights the key property that is common to all topological states of matter. So let's have a look at topological insulators. Imagine this blue rectangle represents a two-dimensional material, and now you would like to apply a voltage to that. If this material would be an insulator, it would not conduct electricity and no current would flow. In contrast, if it would be a metal, it would conduct electricity really well and a current would just flow through it. And that's where it becomes interesting. If the metal would be a two-dimensional topological insulator, it would look more like this. So it would still not conduct electricity in the bulk, but it would conduct electricity on the edge. So it behaves like an insulator in the bulk and like a metal on the edges. This is really peculiar. And in order to understand the origin of this exotic behavior, theoretical physicists have recently come up with a new theory that involves mathematical tools from the field of topology, which is why these materials are called topological insulators. According to the theory, the existence of metallic edges does not depend on microscopic details of the material, but has a topological origin. And here we are at the heart already of topological states of matter in general. So every topological state has a key property. And so in our example, this is the insulating bulk and metallic edge. And this key property has a topological origin, which means that it is robust against perturbations. Topological effects are only observed in very small materials, on the order of micro to several nanometers. A nanometer is a millionth of a millimeter. The physics at this very small length scales is governed by the laws of quantum mechanics. And as these materials are so small, they're really hard to control and manipulate. Now you might ask, okay, where can we find such exotic materials? Sticking to our example of topological insulators, there exist theoretical predictions and experimental confirmation for the existence of materials that really are topological insulators. However, it is desirable to have control over certain properties of the topological material, which is why we are trying to engineer them. Since I'm a theoretical physicist, you might now wonder, okay, what do you mean then by engineering? And so the basic idea is that instead of searching for exotic materials that are topological insulators, we would like to use a combination of conventional materials that produce the same topological state once we bring them together. So you can imagine that when you bring together different kind of materials, they will start to interact. Now you would have to find the right choice for the individual components such that the interaction between them will produce the correct topological state for the whole system. So there exists a plethora of materials, and if you would go for a trial and error method, you would probably never find the right combination. This is why we as theoretical physicists try to predict the right combination of materials. Our predictions are based on solutions to mathematical equations that we derive from the laws of quantum mechanics. The study of topological states of matter is an exciting branch of fundamental research. And the search for new topological materials is driven by the expectation that their exotic properties can be used in future nanotechnologies and quantum computation.